Hello and welcome to another tutorial. Today we'll be doing the topic vectors for the AAHL syllabus. So firstly, we'll start by introducing what vectors are. So vectors are any quantity which have magnitude and direction. This is the mainstream definition of vectors, what you have heard before, magnitude and direction. So the thing is, how do you define a vector? So a vector is basically represented by an arrow like this, an arrow in the plane. So a vector has an originating point and a terminating point. So the originating point is called the tail of the vector and the terminating point is called the head of the vector. Now the thing is, how do you attach a formalism or basically a mathematical framework to the idea of vectors? So we do that by attaching a Cartesian plane to the problem. So if I have a Cartesian plane here, Cartesian plane is basically a 2D plane. Now in the 2D plane, if I'm drawing a random vector here, so I define a vector by its x step and y step. This is basically the x step of the vector and this is the y step of a vector. So a vector is represented in a format like this. You write the x step here and the y step here. This is called the column vector notation. Column vector notation. So if I have a vector which goes 3 units right and 4 units up, so the way I represent this vector is 3, 4. This is basically a column vector notation. And the thing is, it doesn't matter where the vector is in the Cartesian plane because the vector is defined in terms of its x step and y step. So the position of the origin doesn't matter here. I can define the same vector somewhere here as well, somewhere here as well, somewhere here as well. So only the x step and the y step matters in this case. If I have a vector with the x step as A and y step as B, so I define it like this, AB. Now what happens if I scale both the x step and the y step? By scaling, I mean multiplying both the x step and y step by a scale factor k. So that means the x step becomes ka and the new y step becomes kb. In this case, if I try understanding what this angle is with the positive x-axis, I'll label this as theta and this is alpha. So theta is tan inverse b by a. And the thing is, alpha here is tan inverse kb upon ka. If I cancel out k and k, I get tan inverse b by a, which is same as theta. So the thing is, if I scale both the x step and the y step, the resultant vector is actually parallel to the previous vector. So that means if I multiply the x step and the y step, both with a constant k, the resultant vector is parallel to AB. And this is basically called the idea of parallelism. And this is a very important tool which we'll be often using ahead in the chapter. This statement can be written as multiplying a vector with a constant k. Instead of individually showing that we are multiplying the x step and the y step by a constant k, we just show that we are multiplying the whole vector with a constant k. Next thing we define is the magnitude of a vector. So if I have a vector AB like this, so a magnitude is basically defined by a mod like this. So the magnitude is basically the length, and that is nothing but obtained by the Pythagoras theorem. So in this case, for the first vector, the length of the vector is this nothing but root a squared plus b squared. So in this case, it's root a squared plus b squared. Now if I define the magnitude of ka and kb, its length is equal to square root of ka the whole square plus kb the whole square, which is k times root a square plus b square, which is k times the modulus or the magnitude of ab. Instead of writing this whole thing, what we do is we define a vector notation. So in this case, instead of writing a b again and again, what we can do is we can define this a b as a vector d like this. But instead of just writing the alphabet, I have to put a small bar over it as well. Bar with an arrow. So in this case, the same statement for the magnitude can be written as magnitude of d equals root a squared plus b squared. So what I've seen as of now is that I'll just star mark it, that k a bar is always parallel to a bar, where k is greater than 0. And if k is less than 0, you can call it the anti-parallel condition. Basically, it just means that it's pointing in the opposite direction. Sometimes both these definitions are used interchangeably. Parallel and anti-parallel are basically considered the same thing. But in the case of vectors, the thing is there's a direction as well. So we have to be aware of this distinguishing feature of parallel and anti-parallel. So this statement basically means if I have a bar and if I have to understand how 2a bar would look like. So 2a bar would basically point in the same direction with twice the magnitude. Half a bar would point in the same direction with half the magnitude. Sorry. Minus a bar would point in the opposite direction with the same magnitude. Similarly, minus 2a bar would point in the opposite direction with twice the magnitude of the vector. Next is algebraic operations using vectors. And the first operation which we'll do is addition. So addition can be understood in an algebraic manner and more importantly in a geometric manner. So in algebraic manner, suppose I define a vector a bar whose components are a1, a2. As of now, I'm just considering two-dimensional vectors, but the same idea can be extended to three-dimensional vectors as well. So if I have a vector a, which is a1, a2, and a vector b, which is b1, b2. So if I have to add a1, a plus b, so it's nothing but straightforward x component plus x component, which is a1 plus b1, and y component plus y component, which is a2 plus b2. Now, how do I understand geometrically as to how the addition of two vectors a and b look like? So using the algebraic definition, I sort of get a hint of as to how the addition vector looks like. So I'll just randomly represent a bar as a vector and b bar as a vector somewhere else here. So this is a marking the x step, which is a1, and the y step, which is a2, vector b, x step b1, and y step b2. So algebraically, the addition a bar plus b bar has the x component as a1 plus b1, which is addition of the respective x components, and a2 plus b2 as the addition of the respective y components. So that means a bar plus b bar is a new vector whose x component is a1 plus b1 and y component is a2 plus b2. But the thing is, this addition is equivalent to aligning both the vectors a bar and b bar next to each other like this. Now, if I align a bar and b bar next to each other, I can see the total distance from this point to this point here horizontally is nothing but a1 plus b1, and similarly the vertical distances are b2 plus a2. So the thing is, if I have to add two vectors, addition is represented by connecting the tail to the head of the second vector. This is called the triangle law of vector addition. Triangle law. So it can be very easily understood. So if I have a vector A and suppose a vector B pointing here. Now if I have to find the addition or represent the addition of these two vectors, what I'll do is I'll write this as A and I parallelly transport B here. And I can do parallel transport because the thing is vectors are defined irrespective of the origin. So I can just parallelly move B bar here and connect the tail of the first vector with the head of the second vector. So this is a bar plus b bar. This is a geometric way of adding two vectors. Subtraction is also something which follows from addition only. There's nothing new in it. So a vector a bar and again a vector b bar. So if I have to find a bar minus b bar, so in this case, I'll consider or I'll draw how b bar looks like. So minus b bar looks like. So minus b bar is same in magnitude but in opposite direction like this. So this is a and this is minus b. So the addition is this blue vector, which is a bar plus minus b bar, which is a bar minus b bar. So this is how subtraction works.